Okay. I imagine that most of you are probably thinking, thank goodness the homework isn't due today. Well, first off, welcome back, everybody. I hope you all had a relaxing 5 days away from me. And I hope that you didn't have too many professors that said, oh, they have a long weekend, I can give them a bunch of work. You know, that didn't happen at all, did it? No comment. No, I'm sure it did. But you do have a homework. I'll get this out of your way. I'm sorry. You have a homework due on Wednesday. What I'm going to do for the homework is I'm going to post the solution on Thursday, but I want you to have the homework solution at some point. If it was up to me, I would post it like right then and there, but I do have I do allow late submissions. So maybe what I'll do is I'll post it Thursday morning so that you have it. Although I can't believe that this one homework solution would be that consequential, but I do want you to have it in preparation for the exam. In terms of grades, everything's graded up through 4.2. Nothing's due today. Homework 4.3 is due on Wednesday. We review for the exam on Wednesday and we celebrate on Friday. Okay. Exam format will be basically the same format as last time, like same structure, same layout, just it's on this stuff and not on the previous stuff. So, okay. Sound good? Okay. So, I tend to think that our best use of time regarding equilibrium problems in 3D is to just do another one. And I say that because these problems are long. they just are long. And I don't believe that they are substantially difficult. I really don't. But I think that it's really easy to sort of get lost in the weeds of all the calcs that you're doing. I think that probably the most important thing that you can do in this exercise is to plan it out at the beginning. In other words, like the stuff that we did on the board, I'll probably do it here in the class notebook, but the stuff that we did on the board at the very beginning in terms of planning out what we were doing, where we were writing R vectors from, how we were summing moments, all of that, that plan was probably the most important thing that we did. So I'm going to emphasize that today. So we're still, we still have the same equilibrium concepts that we're considering. We still have the same support conditions that we're going to be using. And honestly, I kind of just want to jump right into it. So that's what we're going to do. This is going to be the problem that we focus on during today's lecture. And what it is let me just go ahead and pull the notebook up so it's here. What we have here is a problem very similar to the last one that we did in class. There's a couple caveats in this problem that change things, okay? And I would say that the biggest thing that changes things is what's going on with this cable, this B or DA and BE cable, okay? So let's just sort of take stock of what's being said here in the problem. So we have a 48-inch boom, so that's this pipe here, this AC, so that's our rigid body. We have this pipe here that's being held by a ball and socket joint at point C, okay? So how many reactions are we going to have at point C? If it's a ball and socket joint. It's kind of like a pin in 3D. 3. We're going to have a CX, a CY, and a CZ, right? We're going to have 3 unknowns there at point C, okay? It's being held in place by a cable here and this cable DAE, okay? So what's happening here with this cable here, DAE, is that it's a single cable, right? So maybe I'll do my best to try and illustrate that up here. So what we've got is we have a pipe like that. We have sort of like a loop at the end of that pipe. And we have a single cable that goes like that. So we'll call this point A. Maybe point E goes like that. And point D goes like that. Okay? So if this is the same cable, is there something you can tell me about the forces inside these two, the force AD and force AE? Let me ask it like this. So if I were to draw the free body diagram for the pipe as a whole, okay? So here's the pipe. Okay? So there's going to be an unknown here, so we'll call this CY, CX, CZ. There's this 320-pound load right here. There's an unknown force like that, which we'll call this, this is the force in cable BF. And then there's two forces sort of like that. What can you tell me about the magnitude of these two forces? They're the same. The magnitude in this force is equal to the magnitude in this force because it's the same cable, right? It's the same cable, right? If there's sort of an eye bolt right here, and I slip a rope through that eye bolt and I'm yanking on it, it's the same tension in both sides, right? So the tensile force in this cable and this cable are the same, okay? And that's probably, if you understand that, that's probably really the trickiest part about this whole problem. Okay, so for this loading scenario, what we're going to do is we're going to determine the reaction here at C and the tension in these two cables. Not the tension in the three cables, because it looks like 1, 2, 3 cables, but these two have the same magnitude. We'll have different force vectors, but the same magnitude. Everybody with me so far? Okay, so maybe what we'll do is we'll start off by describing our forces in pounds. Okay. All right. So, like I said, I propose that there is an unknown reaction at C. Okay? So, in terms of the forces that are on this pipe, okay, I propose that there is a C vector, which we'll call CXI plus CYJ plus CZK. Is everybody okay with that? That there's a vector here that has an X component, a Y component, and a Z component, but we don't know what they are. They're unknown reactions. So far, so good? Okay. We have a force that's being applied here, this 320 pounds. Maybe we'll get very inventive and we'll call this F. How would we describe that 320-pound vector numerically? How would we do that?
0, negative 320
You're both saying the same thing, yeah. So you both got it. So 0I minus 320J plus 0K. And why is it negative? Because the y-axis is going up like that. Negative across a different direction. Okay. Now, there are, now like I said, these two have the same magnitude, okay? But here's how I'm going to do this, okay? So I propose that we're going to have a tensile force AD and a tensile force BE. And this is going to be tensile force BF. So there's going to be three vectors. Sorry. Okay. And the way that I'm going to describe this is I'm going to say, okay, I've got three vectors. Now, how do we describe a force vector in 3D? We take its magnitude times its lambda. Yes.
Would the tensile force be BE or AE?
AE. You're right. It's AE. I'm sorry. Thank you. You're right. AE. AE. Okay. Thank you. Yeah, you're right. AE. Okay. Now I've got three different vectors. Okay, now remind me, how do we describe a force vector in 3D? We take its magnitude times its lambda, right? So here's what I'm going to do. I'm going to say this. And notice what I did here. Notice how I'm using the same magnitude for these two, right? Why am I using the same magnitude? Because it's the same cable, right? The idea is that these magnitudes are the same. Okay. Does that make sense? Are we okay with that? Okay. All right. Now let me ask you a question. Okay. So in order for this system to be in equilibrium, it must satisfy both that the sum of forces equals 0 and also that the sum of moments equals 0. So for this system, about which point do you believe we should sum moments?
C.
C, because there's a lot of unknowns going through C and we can make them all go away, right? So I propose, if that's the case, how many R vectors do we need? Like, how many do we actually need? Two, right? We really only need two. We need that vector, and we need that vector, right? That makes life really easy, doesn't it? And these vectors are really easy to write, aren't they? Because it's just going to be 48 what? Z, so 48K and 30K? Is that it? So maybe I'll keep my notation simple, and I'll say, let's call this, I don't know, R1, R2. I'm being lazy today. I don't want to do the, maybe I'll reference what they actually are, like the specific names of them down here, but we'll use R1 and R2 to make our lives a little easier. Okay? Sound good? So if I scroll up about like that, so we have position vector 1, position vector 2. So what we'll do is we'll say position vector 1 is 2A from C. And from now on, I'll probably just use R1. But in case you want that complete in your notes. That's going to be to B from C. Okay. All right. All right. So let's make a couple notes here on the board, and then let's start chugging some stuff out. So, how many cross products are we going to have to evaluate? All right, let's list them out, okay? So where are we summing moments from? Point C? So how many forces do not go through point C? So we have, let's see, how about MAD, right? Which is going to be tension AD, or sorry, nope, I got that backwards. So AD, and what's the R vector? That's going to be R1, right? It'll be R1. We've got MAE. We've got BF, which is R2. Am I missing one?
Force.
The force, the 320, right? So I've got the moment due to that force, which is R2 crossed with that force vector, that applied load of 320 pounds. That's how many cross products I'm going to have to do, right? Am I going to have to do a cross product for the reaction? No. Why? Because I'm going to have the C vector here, but what's the distance?
0.
It's 0, right? This is a 0 vector, so this is 0. So for every one of these force vectors, we need to do a cross product except the first one. Does that make sense? That's the only one we don't need to worry about. Okay? Now, how are we going to do these three? How are we going to do them? Well, how do we describe these? Magnitude times direction, right? So this is going to be the magnitude times that magnitude magnitude. Let's redo that. Okay. All right, so here's my point. I think it's worth just sort of taking a step back and going, okay, what all do we need to do for this problem? Okay? How are we going to get, so let's sort of work backwards. How are we going to get these lambda vectors? The distance vector divided by the magnitude, right? So we'll do that for each of these, evaluate our 4 cross products, and then start summing. Make sense? So we got a little bit of work to do, but let's make sure we sort of have our eye on the prize. Okay. Sound good? All right. Now, in the interest of not scrolling up and down incessantly, let's see. I'm going to put these on the board, and then I'll put them in the notebook here. All right. Let's write these down. I'll write them on the board so I don't have to scroll up and down. If I were to describe AD as a vector, how would I do that? So we're talking about AD. So along the x-axis, what's the term? Negative 20. What about the the y-axis? 0. And what about the z-axis? Sorry, excuse me.
Plus 48.
Is it plus 48 or negative 48? Because we're going from A to D. We're going this way. The positive z-axis goes this way, so it's minus 48. Does that make sense? Okay. Somebody else. Somebody help me with the AE. What about the x-axis? 0. What about the y-axis? Positive 20, right? And what about z? Negative 48. Okay. BF. Positive 16, yes. For Y, it is 0. And then Z, negative 30. Okay. So just so we don't have to do a bunch of scrolling, we now have those. So think about, okay, let's take stock of where we're at right now. Because here's what I propose. From now moving forward, we just got a lot of plug and chug calculations to do, right? Take this, convert it to a unit vector, this, convert it to a unit vector, do some cross products, start summing, right? So hopefully from here on out, what I'm about to do, I can do it a little quickly. It's going to be like a lot of calcs, but it shouldn't be anything that's all that confusing. All right, let's let me recopy these here so that I don't have to scroll like crazy. Okay. All right. So while we're at it, let's go ahead and do put some magnitudes out here. Okay.
AB or AD?
Why do I keep wanting to say AB? I'm in this AB mode. AD, AE, and BF. Okay, so just so we're all awake this morning, how am I going to find these magnitudes? Pythagorean theorem, so 20 squared plus 48 squared and then the root of all that. Would you believe me if I said that this is 52 inches? Would you believe me on that? Would you believe me on this one being also, well, this one also has to be 52 inches. Would you believe me on this one being 34 inches? Is that okay? Okay. So, tell me what to do. What do I need to do with this information? Tell me what my next step is. Boom, get a unit vector by taking the vector divided by its own magnitude. So what we'll do is we'll say, okay, unit vectors unitless. Okay, so these are unitless vectors. All right, so let's take one at a time. There, I did it again. So this is going to be and this is sort of like a deck of cards, like 52, and these are all going into 4, so maybe like 13 in each suit, so maybe like, I don't know, minus 5 over 13i plus 0j minus 12 over 13k. Is that a fair statement? Just keep everything in fractions. And then, so lambda AE and then BF. So let's see. So BF is going to be, let's see. So it's going to be 16 over 34. So 16 over 34 doesn't reduce all that much, but it'll go 8 over 17. Okay. That one goes 15 over 17. Okay. Everybody with me so far? So, hopefully the what we're doing so far is straightforward. Hopefully it's not too challenging, and hopefully I'm hoping it's almost even a little boring, because if it's boring, that means you understand it. So that's a weird thing for a professor to say. I hope you're bored, but if you understand the concept, then you should be relatively good to go. Okay. All right. So now we've got to start doing some moments. Okay. Now we got to start evaluating some moments. So. And these moments are going to be in inch pounds. Okay? All right, so let's just take them one at a time. So let's go with our first one. So our first one, which we said our moment AD is going to be R1 crossed with T AD, which is going to be, we're going to factor the magnitude out. Now the cool thing about these cross products is there's tons of zeros, so it should make our life pretty easy. Okay, so okay. Oh, whoops, I got that backwards. Whoopsie. Lambda goes down here. Can't do that on a physical whiteboard. Okay, so we have R here, the lambda there, and then don't forget our T1 there on the outside. Yeah. Okay. So let's see if we can do this in our heads. Okay, so let's see. So the I term, what do we do? Cross that out basically. So we're doing that times that, which is 0, right? For the J term, that times that, oh, we actually have a value, so it's like 240 over 13, right? But if we do this, so the K term, if we cross that out, we're going to get 0. So the only thing that we're left with is let's see. So it's 48 times 5, which is 240 over 13. That's negative. Maybe we ought to be consistent with that. Let's take our time with that. T1 times minus j, because we've got the negative there. And then what do we got? 0 minus 5 over 13, 48, negative 12 over 13. Because I think we're going to have a bunch of negatives, and we got to make sure we're consistent there. T1 minus j, 0 minus negative 240 over 13. So that's positive, but it still comes out negative. Okay. There's like triple negative there. And if you're wondering where this negative came from, that negative came from right there, what I'm basically doing is I'm saying minus j and some stuff plus k. Right? So there was a negative out here, and so we just evaluate that determinant. Does that make sense? So I think that's probably the hardest part of all these cross products is just tracking the signs. So like a negative and a negative and another negative. So, okay. All right. So MAE. Here, I'm going to drop that down just a bit. So the R is 0048. And the lambda is 0, 5 over 13 minus 12 over 13. And then don't forget the T1. All right. So let's see what we can do. All right. So the I term, cross out that and that. Ooh, we actually have some numbers here. So we have this minus that. And so that's going to be negative. So it's going to be negative. This one's a little more straightforward. That's an I term. What about the J? Cross out this and this. Sorry, cross out this and this, and we have 0 and 0, and then the K, 0 and 0. So far, so good? Okay, that one's easy. What about the BF? So that's R2, BF. Does everybody see what I'm doing so far, especially this part here where I'm saying, okay, we're going to factor out the magnitude? Does that part make sense? Because I'll show you the analogy for this one right here in a second. Okay, and then don't forget the T2. So the R is going to be 0, 0, and 30. And then the lambda is, what was that, 8/17, or 8 over 17? 0 and minus 15 over 17. I think that's how that came out to be. Equals. All right. So for the I term, cross that out, 0 and 0. The j term, oh, we actually have a value here, so I think we get minus, let's see. Did I get that right? Minus 240 over 17? Did I get that right?
I had it as positive. I thought it was I minus the negative 240, like it came out.
Yeah, you're right. That is positive. Thank you. It would be negative inside the parentheses, but then there's another one. Yep. And then the k term is 0. Okay. Maybe what I'll do is just line that up just like that. Okay. Okay. And then lastly, we have the moment due to that force. And if we wanted, so just so everybody's aware, if we wanted, we could say 320 pounds times R2 crossed with lambda sub f, if we wanted to do that. Like, we could be consistent, okay? But what would lambda sub f be? I'm just curious. Anybody know what that would be? What's that? 1, but 1 in what direction? Say it again. In the J, right? So this would just be 0I minus J plus K, right? So here's my point, right? So when we write this out, right? So what I'm going to do is I'm going to say 0, 0, 30. And then our force vector was, what was it? It was 0, minus 320, 0, right? Okay, this is how I'm writing it. I could say this is minus 1 and put the 320 out here. It'd be the same answer, you know? So it doesn't really matter. That's what I was saying, is that if we wanted to do that, which it does, you know, I'm not going to worry about it. So let me put this as 0K, because that was the typo. Okay. This is the only one that's not going to have a variable in it because we know the answer, right? So what do we got for the I term? I term 0, and that's going to be, what is that? 9,600 times I. The J term is going to be 0. K term also 0. Okay. All right. And I want to be crystal clear. Did I do these cross products too fast, or is everybody okay with this? You tell me if there's a step that, like, you don't know where I got a certain value. You tell me if there's a part that lost you. I will go through it happily, because we got time. Everybody good? Okay. All right. So, is everybody caught up? Do you need a second? Okay. All right. Okay. So, now that we've got these, now the only thing really left to do for the whole problem is apply static equilibrium. Okay? Now the thing about static equilibrium for these problems, remember the whole point of, okay, so like let's be clear, let's have thought process here. So why did we sum moments about C? Like, why did we take all our R vectors from C? Why did we sum moments about C? Well, we did that so that we wouldn't have to deal with the C vector throughout all this, right? So when we sum moments, so when we apply static equilibrium, let's sum moments first, right? The whole point of writing the moments this way is to eliminate unknowns. So let's apply the summation of moments first, and let's see if we can make our lives a little easier in terms of solving for unknowns. So here's what I'm going to do. I'm going to write MAD, MAE, MBF, MF, all in a line. And notice how none of these had any K terms. They were all I and J terms. Okay, so let's see. So AD was 0I minus 240 over here. Let's do it like this. Actually, let's do it like this. Plus negative. Let's do it like that. Group all the signs in the parentheses. Okay, AE was, all right, it's negative. Okay, MBF this is 9,600. Okay, and I'm going to cheat a little bit here. Bear with me. Okay. I'm cheating a little bit there. I wanted to line everything out. Okay. So, problems up until now, we probably would have said, let's just break out the Casio FX115 ES Plus, right? Do we need that in this case? You're shaking your head no. Why?
Because there is no this second.
You're both saying, yeah, you're both saying the same thing. There's only one unknown here, right? So let's do this in order, okay? So everything in this box would be summing moments in the x direction, and everything in this box would be summing moments in the y direction. If I look in the x box, I only have one unknown. But if I look in this one, I have two. Let's do this one first. Let's sum moments in the x direction first. Bless you. Let's see. Right? So just add that over, flip, and multiply. What is T1? What does that come out to be? 520. And 520 pounds, right? You see what I did? Just flip and multiply. So now, if we sum moments in the y direction, or about the y-axis, so all we've got to do is solve. So T2 is going to be, what is that? 240 times 520 over 13, and then 17 over 240. So the 240s are going to cancel, and what does T2 equal? That's 520 over 13, so that's going to be 40. 40 times 17 is 680. Did I do that right? Okay. So we've got the tension in the two cables. Can somebody tell me what's left for the whole problem? The reaction at C. That's the only thing we don't know. And how do we solve for the reaction at C? What do we do? Sum all the force vectors. Exactly right. So now all we'll do is sum the force vectors. Can I scroll up? So now if we sum all the force vectors, so now we just got to write some stuff out. So we have the C vector. We have the force vector from that 320 pounds. Then we're going to have TAD. We're starting to run short on time, so I'm going to do something real quick. These three we're just going to do that. And we now have the magnitude. So like for example, TBF, we're just going to take 680 times that lambda. And so when we do that, we get, and the same thing for all of them, we're going to get this one's 0I. And this one's that one's that. So all we have to do just sum these up. And that's going to be pretty easy because, like, for example, if we look at the x column, I'm going to get CX, what is that, negative 200 plus 320, so CX plus 120 equals 0. So CX is minus 120. So basically just add all these up, flip the sign. That's going to be your answer. So therefore, C is going to be, that's 120. This one's positive 120. And this one is, so 480 and 480 and 600 is going to be 1560. And then flip the sign, so 1560. Okay. Then don't forget that T1 is 520 pounds. T2 is 680 pounds. I'll say one closing point before we call it. But before I close this, does this make sense? Anybody have any questions? All right, two closing points. Okay. First closing point is that that's it for the coverage on exam 2. In other words, exam 2 is everything from exam 1 up until this moment right here. No pun intended. This moment. The other thing I'll mention that I'm sure is brewing in the back of everybody's head is the following. I do still apply a rule of 3, so I understand that you have an exam where you only have 50 minutes, and these problems are long. I get it, okay? And I've taken that into account when I made the exam. So the exam is not 100 cross products over and over again. That's not what it is, okay? I promise. It is not a time-critical exam, I promise. Come prepared with questions on Wednesday. That's all I got, everybody.